I welcome everyone who has joined us. Practice number 3 today. We study excitability tissues and electrical potential in tissues. Today we will talk about the history of the discovery of electricity in living tissues and watch a video of laboratory work that are experiments of the 18th century. On this slide you see a portrait of Italian scientist Luigi Galvani, and I will leave a link to the video that will talk about his discoveries, and you can just read the text about it. He was the first who discovered the presence and electricity and electrical potential in tissues. This is a monument in the city of Bologna in Italy to this scientist. But at first Galvani's research was rejected. At that time electricity was widely studied. The scientist Alessandro Volta was skeptical to experiments of Galvani. Volta studied different metals and he makes the first battery. He did not consider Galvani's experiments reliable because of the use of metal tools. It was the first experiment of Galvani, and Galvani in this experiment used two metals. It was copper and zinc. On this slide we see a description of the work from our practice book. Let's take a video at the recording of the lab. So, in our laboratory we take the hook from the copper and zinc plasting. In this time, a nerve system generates a potential, action potential, and this potential move in muscle cells, and muscle cells start to contract. In response to this, Galvani used only glass instruments for preparation of rock and carried out the second experiment without metal. Its experiment damaged biocurettes. In this experiment, he showed the difference in potential between damaged muscle and nerve and damaged part of the muscle. Let's see the video. We take only muscle and nerve and damaged part of the muscle. In this place, muscle will be charged negative. We use only glass tools without any metal. And you see the contraction of the muscle. It was the second experiment of Galvani. In future, Galvani's research was approved. This scientist, Matteucci, provided the excitance of electricity and the ability of nerve fibers to conduct electricity current. Let's see the video of lab work. Take two rheoscopic legs of frog. And connect each other by the nerve. Irritate the nerve of first leg, and you will see the conduction of electricity and two legs move together. So nerve of the first leg conducts the moves the electricity on the second one. So these studies confirmed the presence of electrical signals in the body and that these currents can control tissues. I want to show a video that shows the conduction of the action potential through the body of a frog, through the spinal cord, to many muscles. Let's see the video.
So, I think this is it right here. So you're gonna have to try to put a pin in here.
As usual, the first preparation of the nerve.
You guys can see this right here, white. Right? So then if we cut it, we won't be able to stimulate it. Try it.
And contact with the electricity. You see?
right? They got to be a certain amount of voltage. If you keep doing it over and over, it gets tired. So remember how you like ran today? Who ran today a lot? You did.
I did.
And you guys, all you did in physical education, you get tired. Your muscles get tired, and you can no longer move, right? You can no longer move your legs, your arms. You don't want to lift them. You just want to stand there. Same thing with the frog. So this voltage might be a little too much for it. Does that make sense? So the muscle fatigues very fast. So therefore, that's why we got the contraction in the beginning, but we're not getting contraction anymore because the frog is tired.
Let's try again.
So if the frog is tired, so hey, would you mind grabbing the salt? Let's see if that helps. So why do you guys think salt will work if we put some salt on?
Oh,
It's sodium.
I know
you know
it's
why
salt.
it's sodium?
What do you think, honey? The sodium gives off energy.
In a way, right? It does. What it does, it helps action potentials to happen in your body. To be more precise.
They want to move the salt on the body of the frog. The addition of sodium chloride allows you to enhance the action, and we will see the mechanism later. Adjust the salt. It we use in a cooking.
Actually, you guys know how much is
Yeah, really? Oh, no,
that's why I'm salty now. Like my frog is salty.
Keep it breaded. Let's have it breaded. I like frog legs. It's like, it's moving.
Okay, I put on.
Oh! Ah! Ah!
And so electricity moves through all body. Well, let's look at the signal transmission mechanism.
Pain you experience when you burn your hand results so quickly in an action by your muscles. Many animals respond to environmental stimuli using specialized cells called neurons. A stimulus is detected by sensory receptors, and the body responds through motor effectors. These cells working together allow you to respond very quickly to threats. When you touch something hot, heat receptors of a sensory neuron detect the stimuli and send the information of heat to an interneuron in your central nervous system. From there, a motor neuron sends a response from your central nervous system to the skeletal muscles in your arm, causing them to contract and pull your hand away. The fundamental process of neural transmission that underlies this action occurs in all neurons of the body. Neurons transmit this information through changes in the electrical potential of the membrane by the movement of ions across the membrane. An electrochemical gradient governs the movement of these ions, resulting in an electrical impulse. The resting membrane potential in a neuron, when the cell is not firing an impulse, is established by the unequal distribution of sodium ions outside of the cell and potassium ions inside the cell, making the outside of the cell more positively charged compared to the inside. The electrochemical gradient is established and maintained by an enzyme called sodium-potassium ATPase. When a neuron is stimulated, sodium ion channels open and sodium ions flow into the cell. This leads to a change in the electrical potential across the membrane called depolarization. The depolarizing electrical potential travels down the dendrites and over the cell body. Multiple electrical potentials will combine at the axon hillock in a process called summation. If the depolarization is large enough, an action potential is triggered. Action potentials are all or none electrical impulses that maintain their amplitude and strength down the length of the axon. The action potential travels down the axon when the depolarization of an area of membrane causes adjacent voltage-gated sodium ion channels to open. The influx of sodium ions results in membrane depolarization along the membrane. After a short delay, potassium ion channels open and potassium ions flow out, repolarizing the membrane. For the neuron to fire again, the resting membrane potential needs to be re-established. Sodium-potassium ATPase is used to move sodium and potassium ions against their establishing the resting membrane potential. As the action potential moves down the axon, ions are diffusing only a short distance, allowing the signal to move quickly. At the axon terminal, the electrical impulse passes to another cell at a cellular connection called a synapse. The space between the presynaptic neuron and a postsynaptic cell is called the synaptic cleft. The presynaptic neuron contains signal molecules called neurotransmitters that are packaged inside vesicles. When an action potential reaches the end of a neuron, neurotransmitters are released by exocytosis from the neuron into the synaptic cleft. Neurotransmitters bind to the adjacent cell at receptor sites attached to ion channels. The channels open, allowing the movement of ions into or out of the effector cell, which alters its membrane potential, thereby transmitting the signal from the neuron to the effector cell. Because nerve impulses move very rapidly down the axon of a neuron and move from cell to cell across synapses, you react quickly to a stimulus, like burning your finger.
So, before you watch the video about Galvani's work, I want to remind you about homework. In your practical notebook, you should read the pages 67 to 71, and after that finish the protocol to lab work 17. In book Animal Physiology, you should read the pages about neuronal physiology, and on our page in a Moodle on our site you should do test 1.3 electronic potential in cells. So it is almost all for today, but I watch with you video about Galvani's experiment, and let's watch the video.
How did Galvani make a dead frog jump? And how did that lead to the battery? And hey, didn't a guy named Volta invent the battery? Well, I'll tell you, and along the way, I'll talk about professional misconduct, a surprising accident, the inspiration for Frankenstein, and the building blocks of life. Ready? Let's go! Electricity, 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 electricity. Sometime in 1790 or 1791, an Italian anatomy professor named Luigi Galvani was playing with electricity machines and hoping to find something interesting to publish. See, Galvani was a member of the Academy of Sciences, the Institute of Bologna, and he needed to submit a research paper every year. For the previous 4 years, he he had published research on the hearing of various animals. However, that year his work was stolen by a rival, so he needed a new research subject, and quickly. Therefore, he turned to the newish subject of electricity and got several assistants to help him. He had static electricity machines that you could spin to produce large static charges, and jars called Leyden jars that could store the charge and give it a terrifying jolt when you connected them in a circuit. One day, unrelated to his electricity experiments, he happened to put a dissected headless frog on the table while his assistants were running these electrical experiments. He never said why he was cutting up frogs in the first place. A popular myth is that he was making frog soup for his sick wife. However, it seems much more likely that he was dissecting the frog for an anatomy lecture. He was an anatomy professor after all. Anyway, there was a dissected frog on the table. Here is how Galvani described what happened next. Quote, I had dissected and prepared a frog, and I had put it on a table where there was an electric machine. As soon as one of my aides, by accident, touched the internal nerves of the frog with a scalpel, at once he saw all the muscles go into violent convulsions. Galvani was deeply surprised to see the headless frog jumping, and did a series of bizarre and macabre experiments, like frogs in a jar and frogs in a circle, to determine what would make the frog dance. Galvani, or honestly his assistant, discovered two things with this experiment. First, they found that frog legs are an extremely sensitive machine for sensing electricity, superior by a factor of 5,000 to anything non-biological available at the time. Secondly, and more importantly, Galvani started the study of how electricity works in living systems. He found that muscles contract with electricity and nerves send messages with electricity. In truth, electricity is the building block of living systems. We think with electricity, we hear and see and smell with electricity, our hearts pump with electricity, and our muscles move with electricity. This is not just true for frogs. All animals' biological systems are electrically based. Now, it took a further 150 years to truly understand the complex beauty of the biological system, but Galvani started us on that path. Galvani then decided to move his frog experiments outside to see if thunderclouds could make the frog jump as well as static electricity would. This was 38 years after Benjamin Franklin flew his kite in a storm, so he's not surprised at all to find the frog jump theatrically in thunderstorms. However, something else happened that was truly unexpected. Sometimes the frog would jump on clear days with no static electricity or atmospheric electricity involved at all. What was going on? At first, Galvani wondered if the frog stored electricity from past atmospheric storms. However, soon he realized it had nothing to do with the weather. It had everything to do with his garden. See, Galvani had iron railings surrounding the garden that he hooked his frogs on. He also used copper hooks to transport the frogs. It was this combination, the iron and the copper, that caused the frog to convulse. When he took the frog inside, he could make a frog dance with just a piece of copper and iron. Crazy, huh? This is a major find. Putting copper and iron into a frog produces electricity with no rubbing globes or thunderstorms in sight. Galvani decided that the frog moved because it had been alive in the past. He thought he was reanimating the frog, a la Frankenstein, whose author was inspired by Galvani's research, by the way. Galvani published his work in 1791, and it was an international sensation, especially among anatomists. Suddenly, there was a way of studying how muscles move and how nerves communicate. He had connected electricity to what makes things alive. He had made the spark of life literal. Galvani didn't know it, but he had also invented the first battery. The acid in the frog leg reacted with the copper to add electrons and reacted with the iron to remove electrons. The electrons then flowed through the frog leg from the copper to the iron, making the frog leg jump. In terms of physics, it was a completely useless battery as it discharged inside itself. This is why most people don't consider his invention a battery. However, there was a man named Alessandro Volta who was supposed to be Italy's leading expert on electricity. he became obsessed with jealousy over Galvani's fame, which led him to inventing the first non-biological battery. This was the battery that changed the world. And that is why batteries are measured in volts in his honor. And that crazy story is next time on The Secret History of Electricity. Thanks for watching my video. Please remember to give it a nice thumbs up. Also, make sure to check out that video about how Volta invented the battery. It's a good story. Finally, if you want to know how a modern battery works, watch my video, How a Battery Works, a simple explanation for adults. And make sure to join my YouTube page called Kathy Loves Physics, my Facebook page called Kathy Loves Physics,